Hello, everybody. Good evening. Welcome. Thank you for joining me. We always say if you're new, let us know where you're from and say hi in the chat. Or if you're a return viewer, say hi also. Good to see everybody. Yasmin, welcome. Javier, congrats on catching up with the live lessons. Good job. Makes me feel good about streaming these once a week. Good to have you back. As always, Mom's the most popular here, and that's all right. It's a busy time for us at Carnegie Mellon. Admissions season is upon us. We have all of our applicants right now applying. We have a high school program that we run every summer, which is great. It's like the most fun I get to have as an in-person educator because we bring in like 100 students from across the U.S., but also we have quite a few international students every year. And they come and they stay with us for about 4 weeks on campus, and we do full-time study with them at the intersection of a little bit of experimental biology and a little bit of computational biology too. And so that's really cool. We're probably going to go over 100 students this year for the first time, I'm hoping. And it's just meant we've had a lot of applications to review from a lot of really talented students. And then we also have our undergraduate program is growing. And that's been super exciting. So we're having all kinds of admissions events for our students who have been accepted. So they've been coming in to visit. And we've got like a record number of computational biology students who are going to be coming to CMU. So that's all been thrilling. It's been cool to meet them, meet their parents, have them in class, all that good stuff. And we're looking forward to the fall. And also on top of that, we have Jensen Huang's going to be our commencement speaker, which is really cool. And he has a couple of really good quotes that I've been using of late. Number one is he said, a few months ago, they were asking him, what do you think the next big revolution is going to be? And he said, without a shadow of a doubt, it's going to be what he called digital biology. So that's about as good of a sales pitch for my computational biology course that I'm going to teach on here as I can have. Look out for some announcements about that in terms of timing and how everything's going to work. But, his other quote that he had that I saw today was, he's talking about the fact that they have a lot of engineers at NVIDIA and that, he doesn't think of what any of them do as coding. And I'm also always, even when coding was a very popular word, it's not really a word that I used a whole lot. I always have preferred the term programming. And I think that even if you're using Claude or you're using an AI model to produce something for you that involves code, that's still very much programming. Programming is clearly and coherently telling a computer what to do, and that could involve typing out code. It also could involve, making sure that your prompts make sense and ensuring that this communication works, so that ensuring that what you're getting back from it is reflective of the model that you want to build. And along the lines of solving problems, I think as we've gotten into these more advanced questions, we have started to see problems that are like, that are like truly real problems that on the coding level, we have to build up a fair amount. And I think there's still a lot of value in understanding kind of how does all of the rubber meet the road in terms of the code itself, right? But once we get towards these more complex applications and we have the foundation of the code syntax down, then it's just a matter of saying, what are the kinds of things that we can build with this? And so that's what's exciting about teaching this course and how it hopefully is going to change in the future, both online and in person, is we'll move away from syntax and coding and these sorts of things. What does it mean for you to take a programming course in 2026 when you have all these tools at your disposal? So we'll make sure you're connected with us and everything in all of our platforms, because we'll have a lot more to say about this as the course evolves. And yeah, I'm excited to continue teaching this in an era where everything is changing so rapidly. Krishna starter code. I put starter code in an email, and so if you're on our email list, that's a great reason to be on it. You'll get an email in advance, and I sent that around previously. I also just put a link to I think it's probably in the description of the video. If it's not, we'll get that updated. But the starter code is a link that's accessible in the page on our Programming for Lovers website, where you can see, like the second paragraph or something, there's a link to grab our starter code. And I've got that here as in a UPGMA folder that I just put into Python SRC. So UPGMA is a good example of the value of seeing, not just learning to code, not just knowing the syntax of a language and how to manually type in things like linked lists or something like that. Like, there's so much more to programming and computation than all that stuff that I think a lot of folks have thought of when they think of computer science. These days, everything is just so broad, and it's why we have so much success with growing our own academic programs, because computation is touching on every aspect of life. But when you look at something like biology, it's honestly fascinating to go back and look at something that we're going to do today, and that in many cases is very fundamental. It's an algorithm that was at the foundation of an entire area of computational biology, which is how do we make trees. And when you look at the original paper was in something like the University of Kansas Scientific Bulletin. And you can go and find it. It's got tens of thousands of citations because it helped to launch an entire field. But it is practically indecipherable as something that is involved in an area of computational science where we have certain ways of explaining things. And I mean, if you think about how this course works we've got an entire website that often explains things on the level of pseudocode and frames problems in terms of clearly defined inputs and outputs that then later go into a function. The paper is like completely divested from any sort of framing in this way. And so there is this huge benefit these days still in looking at a scientific discipline from the lens of computation, because ultimately the problem that we're trying to solve is trying to produce a scientific answer. And I'll say a little more of that when I show our starter code directory here, because there's tons of different questions that we could answer, all related to this one particular application. But where you get an entire field from is when you start asking questions like, when is it that this doesn't work? What are the exceptions to this? When is this particular algorithm strong in certain ways? And I'd say that's another pointer for the type of thing that we do when we dig into an entire field like computational biology, is to understand how when the data change, how is it that changes the problem that it is we're going to solve, and how do our algorithms need to adapt as well. So this has quite a bit of, I would say, what we do here is the closest to what it would be like when I try to teach the discipline of computational biology, and same for many of my colleagues. So we'll see that as we go. And as a result, I think what we're going to do this time is going to be a little bit different, in that I want to walk through an example just to explain the algorithm. I think in a lot of cases, the algorithm itself, we can kind of code and appreciate as we go through the coding process. But I'm going to show a couple examples here, and make sure that we understand and appreciate the algorithm, which of course is on our Programming for Lovers website. You can check out an explanation of all this, but it's, I think, going to be fruitful for me to walk through a little bit of an example. So that is where we are going to start. And then I'm going to walk through our starter code directory here too. And then I'll say a little bit more about how is it that this idea, how is it going to connect to an implementation that we have? Because what we've seen previously is we've got a good sense of how to, understand an algorithm, but we may, as things become more advanced, it may become a little bit of a challenge to take that idea of an algorithm and convert it into an implementation. And seeing that, I think, has quite a bit of power. So we're going to look at an example. All right, BZ, welcome. What does Jensen mean by digital biology? I think he just doesn't know that that's not what we call it. Like, I think he's excited about the fact that there's huge areas of open questions in everything from the design of new drugs to building a virtual cell and being able to run experiments on a cell where the cell lives on a computer, human longevity, cancer treatments. Like, a lot of these problems are still very much unsolved. And I think there will be, you pick any one of those areas, and if we see large changes in them, I think that'll be a revolution. And Yasmin, AlphaFold's a great example because, I was talking to my students about AlphaFold the other day, and if you stick around with me for my great ideas in Comp Bio course, we'll talk about AlphaFold in it, of course, because it is a great idea. But also, it's kind of like it's only the start. So AlphaFold will give you a good prediction of what the structure of a protein is. And that's nice. It has tons of applications. I think there are potential downstream ramifications of it. For one, it needs to become more accurate to really be like replaceable in terms of we're never going to run an experiment again. It's not quite there. But just because you can predict the structure of something alone doesn't necessarily mean you have cracked an enormous potential application of that problem. It just leads to a lot of other things. So we were talking about this with our students the other day. You can predict the structure of a protein, sure, but what if you do start doing things like, I don't know, forming proteins that have structures that are outside of anything that's known in nature? The space of all possible proteins is huge, and the collection of proteins that occur in nature is one small component of that. So a lot of people, for example, are trying to look into, so many medications that we have are because of serendipity in terms of studying nature and being able to capture this known protein. What if we understood the language of proteins and instead then just started designing synthetic proteins that became the medications of tomorrow? Examples like that are why, sure, everybody's heard of AlphaFold, but the frontier is still very much expanding in front of us. All right. Now, that's it for that. Hopefully I've got you excited about taking that course. Again, make sure you're on our email list. That's useful for a lot of reasons, but I'll be having more information coming soon about that. Of course, right now we're focusing on these streams and finishing up part 2 of our Programming for Lovers streams, and we've been doing our Roslyn streams on Thursdays. So join us for all of that. Make sure you're in touch with us, subscribe, everything. In the meantime, I'm going to show you a walkthrough of the UPGMA algorithm, and then we'll come back here and do some coding after we understand how we take that algorithm and actually are going to implement it. As always, if you have any questions, let me know. All right. So we looked at UPGMA, if you followed the reading that accompanies this. And I want to just, on a high level, talk a little bit about how this algorithm works. So we could imagine we have 4 species. I think the fancy term is taxa. And we're going to call them I, J, K, and L. So we've got a matrix where all the values in that matrix represent the distance between the corresponding values. So the matrix is saying here that the distance from I to K, for example, is equal to 4, but the distance from I to J is equal to 3. So this is a small, contrived example, but it is a valid distance matrix. And if you follow our reading, one of the things that you'll learn is, even though it looks simple, it's got these small values in it, there actually isn't a tree that you can make that fits this matrix in the sense that the distance between, if you add up the edge weights connecting any 2 nodes in the tree, it's always going to be equal to whatever the value is in the matrix. So you might get some of the values right, but it's not possible that you're always going to be able to say, pick a favorite value like this I to k. Well, you know that the distance between them in the tree is going to be 4. So for now, I want to show how UPGMA works, because the idea is, the fancy term that we use is heuristic. This does not solve any particular problem precisely. As I mentioned briefly, if you go back and you look at this original paper, it's not framed in the language of computation at all. And so let's take the opportunity to bring it up kind of more towards the modern era and explain how the algorithm works. And at its core, this algorithm, which is called something different in a different field. So in the field of machine learning, this algorithm is essentially known as hierarchical clustering. And it's thought of as a clustering heuristic. And what we mean by that is that we start by assuming every one of our taxa, every one of these like present day species that we have, are going to constitute a 1-element cluster, and they represent a single leaf. And so I'm going to take I, J, K, and L. I'm going to assign them all to a leaf. And I'm going to say we're going to call their ages 0. Then what we're going to do is I'm going to progressively find the 2 closest elements according to what the distance matrix is. I'm going to try and find these 2 closest things. And then once I've found them, I'm going to say, well, what's the value? It says it's 2 in the matrix. I will merge them together into a single element. And by how I'm visualizing this, that means I'm going to take their nodes and I'm going to join them together into a parent node. And I will set the age of that parent node to say, like, how long ago was this, are we representing this node to have existed? I'm going to set its age equal to whatever the half the distance is between, in this case, K and L. And so when I assign the age of this node to be 1, because these nodes have age equal to 0, well, we can subtract the ages to tell us what these edge weights need to be. So this becomes a 1, this becomes a 1. And you'll notice that we have a distance of 2 between K and L here, and we have a distance of 2 between K and L when we look at our evolutionary tree that we're making. So far, so good. The distance between these things in the tree is the same thing as what we would see when we look at the matrix. Then the question becomes, what do we do now? So I found these 2 things that I think are probably close. And then we're going to say, well, we want to iterate this process in some way. And so how we do that is to update the distance matrix by taking the average of the distance from any element to the things that we joined together. So I'll go back and show you that in this particular case, we have this cluster of elements containing K and L. And you might wonder, where does this distance from I to KL come from, and where does this distance from J to KL come from? Well, if we look at our original matrix, the distance from I to K is 4, I to L is 3. The average of those is 3.5. The distance from J to K is 4, and the distance from J to L is 5. The average of those is 4.5. So when I compute this distance, these distances here to this cluster, I'm just averaging the distances that I've already seen. The idea here is a common one that I think we see in a lot of algorithms, which is I started with something that has n things in it. So n rows, n columns. And now I've got something, a matrix, that has n minus 1 things in it. So I can just repeat this process multiple times until the matrix shrinks down and there's only 1 thing left. Then we say, what is it that I did at the first step? I looked for the smallest element in the matrix. In that case, in this particular case, it's 3. I said, well, I'm joining I and J together. So we have 2 single element clusters that are getting joined together. And the node that connects I and J is, I'm going to call it IJ. You note I've drawn it a little bit higher over here. And the reason why is that now when I assign the age of this node, I'm still going to say it has age equal to 1/2 of whatever value comes from the matrix. So when I assign this age to be equal to 1/2, it automatically makes this edge equal to 1/2 and this edge equal to 1/2 because I'm subtracting these ages, 1.5 minus 0. And you'll notice that again, well, I have the distance from I to J in the tree is 3. And that's the same thing as what we see in the matrix. So that matches the matrix value that we saw. we're going to iterate this process again. And when I go from here to here, the question is, how did I get 4? Well, we joined I and j together. So the distance from the cluster ij to the cluster kl is to say, well, what was the distance from I to this cluster? It was 3.5. What was the distance from j to this cluster? It was 4.5. So if we're going to join these two things together, now I know that the distance from the cluster ij to the cluster kl is the average of these two values, which is just equal to 4. Now we're down to a 2 by 2 matrix, and we have just one more step. And that one more step says, let's find the minimum element. What is it? It's 4. That was an easy one. We're going to form a new node, and it's going to connect to the two clusters that we're representing here, ij and kl. So now I'm going to have a new node that sits above them, and that connects to the two nodes that I had previously. Its age is going to be equal to 2. Why? That's half of 4. And then we're going to easily get these edge weights here of 0.5 and 1 by subtracting 2 minus 1.5 and 2 minus 1. So the nodes all get labels, and then the edge weights here are just the differences between the ages of the nodes that they connect. And at the end of the day, we wind up with a tree. And when we have this tree, we say, I told you there's no tree that fits it perfectly, fits that original matrix perfectly. But one question that you might have is, why is that the case? I can summarize my steps that I take. Here is the tree that I obtained. Here is the matrix that we started with. And although it's the case that some values in the matrix are equal to their corresponding distances in the tree, that's not the case for everybody. So, for example, the distance from k to l is 2 in the matrix. And now I have a tree where the distance from k to l is 2. Why? Because I go edge weight of 1, edge weight of 1. Similarly, the distance from I to k is 4 in the matrix. And it's 4 over here. So I can go 1.5, 0.5, 1, and 1. Adding up the edge weights is going to be the distance in the tree. So this distance matching the distance over here is good. And one more value I would give you is I to j. So I to j is 3 in the matrix, but then it's 3 in the tree as well. So it might seem like we've produced a tree that is a perfect fit for the matrix, but when we look at other values, we see that's not necessarily true. So the distance from I to L in the matrix is equal to 3, but when we look at the tree, we have this distance that's equal to 1.5 plus 0.5 plus 1 plus 1. So the distance in the tree is equal to 4, and as a result, we have overstated what the distance was that we measured in the distance matrix. And there are a lot of ways that you can form a distance matrix from a collection of biological data. That's a subject of a discussion for another time. But the idea is once we produce one of these matrices, we can always produce a tree corresponding to it. And even if it doesn't fit every single pair of values perfectly, the idea of UPGMA is that it's going to sometimes overestimate the value in the matrix, sometimes underestimate the value in the matrix, but it will provide a reasonable average case for producing a tree from a matrix. Now, I think it's a great opportunity to just take a short moment, and if you haven't had a chance to do this exercise yet, to see if you can follow the steps that I laid out, which correspond to finding the min element, connecting nodes, the nodes that it connects, and having a parent node of those two nodes that it connects that has age equal to a half of whatever the value is. So I'll give you a hint. We're going to be starting with this value of 8 as our minimum. And then I'll give you a few minutes to see, can you get the tree produced by UPGMA that corresponds to this matrix? I'll be here if you have any questions, and I'd be happy to show you a slide or two from what we did. But I kind of want to give this exercise just so before we code anything, we appreciate some important aspects of how the algorithm works. And so you'll see in a second, I'm giving this particular data set for a reason. But for now, I think it's just an opportunity to play around with it. Remy, good question. How strong of a biology or programming background are you going to need for my class when we talk about comp bio? What I'm trying to, the way I want to set it up is to say you probably don't need a lot of biology. I think I'm teaching biology, but just from the lens of computation. For programming, it's always good to have some experience with like algorithmic thinking. I think if you're here and you're taking this class, that's going to give you a really good foundation for it. We'll probably also have an opportunity for you to implement some of the algorithms that you encounter, because we have quite a few like auto-graded exercises that come from our bioinformatics algorithms project that I want to make sure that people have access to if they're interested in that. But it won't be a requirement that you code anything. I think we're going to move that course really in the direction of saying you can code things if you like, but it's the algorithms themselves that are the unit of currency that we care about. And I'll show the steps of the algorithm. Let me even walk through this again. Remember, our steps are single element cluster, and then you constantly find the minimum, connect the two things that it connects from the matrix, assign the age equal to 1/2 of what you see, and average away the two things that you join. So I joined together K and L here. That means I to KL is the average of 4 and 3, and J to KL is the average of 4 and 5. And then we just iterate. Minimum element. Join them together. Average everything. Minimum element. And then connect. And we'll look at this for a couple more minutes. BZ, you're learning deep learning. That's cool. Yeah, that was my lecture actually today to students, was what are the foundations of neural networks? And we go from the very foundations up to deep learning in just a couple lectures, which is cool. It's also nice because it's the perfect example of biology kind of informing an algorithm, right? The weirdest possible loop is you have humans then look at their own nervous system and build something on a computer that tries to mimic that. And then you can take that model that you made and then turn it back on itself and start answering questions about biological data sets. So I've always found that to be a really cool kind of feedback loop, especially as everything becomes more and more powerful. But it turns out deep learning has not really, as a field, it's not really had a huge impact in computational biology in some areas. And one of the areas in which it really hasn't had a huge amount of impact is in evolutionary tree construction, funnily enough. So a lot of the algorithms that people apply day to day might be kind of old school approaches, or things that are based around like maximum likelihood, or approaches like this, but that are not actually deep learning based. At least not yet. Okay. Everything in biology is computational, Richard. Yeah, that's true. There was an article that said that about 10 years ago, and at the time it was very controversial, and I just think there's no more controversy. The take is no longer hot. Everything that we're going to discover is going to come from automation of research and very large data sets. Cool. Let me show you the answer here. So I'm just going to follow these same steps and say find the minimum element, K to L. So let's join them. What's the age of that thing? Should be 4. Average the elements that we're looking at. So when I go from I to this new cluster K and L, should be the average of 9 and 11, which is 10. The distance from J to KL should be the average of 17 and 11, which is 14. Now we have a 3x3 matrix, and we iterate this process again. So we say, what's the minimum element? It's 10. What does that connect? It connects I to KL. So now we're going to have I as one of the elements, and KL is one of the child nodes. So previously we were only connecting 2 nodes at a time. Now I'm connecting 1 node on the left to an internal node that I already have on the right. And so when the age of this parent node gets set to 5, this edge is going to be 5, but this edge is going to be 5 minus this age of 4, which is equal to 1. Then we iterate one more time, and I need to say, well, the only thing left is to join I and KL together. So I need to know what's the distance from J to the cluster containing I, K, and L. And you look at that and you say, that's easy. It's the average of 20 and 14, which is 17. And now I could say, well, I've got one element here, and the age is going to need to be half of 17, which is 8.5, but there's an issue with that. The question is, that's not right. And you might have found that, and if you did, that's okay. But I always use that as an opportunity to point out that in this particular case, we have resulted in an incorrect analysis. So my question for you is, why is that? Everything seems reasonable, right? So what did I do wrong? Is everything right here? Did I make, what am I getting at? What was my mistake? I'll give you a hint, it was in the each node has only 2 children. Now that's definitely good. Demcav says, what about the averaging of the distances? Yeah, and I think that's hinting at what I have incorporated here as an issue. So when we computed this distance from J to this new cluster, why am I joining I, K, and L? Where the minimum element that I found before is the 10. So this node here is the cluster containing I, K, and L. And when we join them together, there's only one distance left. It's J to whatever is remaining. So I averaged 20 and 14. The problem is there's like an election analogy here. Going back to our election simulator from part 1 of the course, where we saw, well, if you're in a U.S. presidential election, some states are going to get more votes than others. And so that's reasonable because it's based off of population. And as a result, in this case, I want you to think about, well, the distance from J to this cluster containing I and KL, we've allowed these two things to have equal weighting. So I've weighted 20 and 14 equally when I computed the average. But that doesn't make sense because this cluster has two elements in it, and I've already produced that 14 as the result of averaging. When I went from here to here, it's because I took the distance from J to the cluster KL is equal to 14 by averaging this already. And so if we looked at our original matrix and said, I wanted to know what the distance from J to the cluster containing I, K, and L is, I would get a different value than 17. I would say, well, it's 20 plus 17 plus 11, all divided by 3. So when I add that up, it's 48 divided by 3, which gives me a 16. And so that value doesn't really agree with what I have because I've done this repeated averaging where something could have 100 elements in it, and its distance is going to count the same as something that has one element in it. So again, when we look back at this and look at our original matrix, this average distance from J to I, K, and L is 16, not 17. And the question becomes, well, one of the things I could do to resolve this is to constantly look back at the original matrix, but how my algorithm is going to work is to use the updated matrix. And it turns out I can solve this problem by looking at the updated matrix. I just need to make sure that I take a weighted average. So if I'm computing the distance from J to the cluster containing I, K, and L, well, this distance here represents a cluster that contains two nodes. And so as a result, it should get double the weight. It should be as if it gets 2 votes, whereas this distance should only get a single vote. And so as a result, I'll weight the 20 by 1, and I'll weight this value of 14 with 2. And after I perform that weighted sum, I'm going to divide by the total number of elements, which is 1 plus 2. So after that, I get 2 times 14 plus 20 divided by 3, which lo and behold is equal to 48 over 3, which is equal to 16. So I'm sort of untangling any averages that I've already computed. That's all really good because it means that I'm still going to allow the matrix to get smaller and smaller. I don't need to look back at my original matrix, but every time I compute this updated distance, I want to make sure that I understand that I need to perform this as a weighted average compared to the size of the clusters that we have. It's the importance of understanding how an algorithm works on the ground level so that we don't incorporate any bias into it. And that would be very easy to do, but we as humans still have the ability to appreciate, especially with respect to small test cases, instances where something like this can go awry if we're not careful. So as a result of this, we know that the better value should be 16 for this distance from J to IKL. And when I finish the tree, I form a new node. That's the parent of this node that I had before, and J. I assign it an age of 8, which makes this distance 8, and this edge equal to 8 minus 5, or 3. As a result, I now have a complete tree. And I'm nearly ready to implement the algorithm, but I probably should appreciate how I take this idea, and then I convert this idea into code. So if we look at our UPGMA algorithm, it kind of fits on one slide, but I like showing all of our subroutines that I'm going to call, and they're highlighted here in green, to indicate that it's still a sizable algorithm, but we're going to be clever about making sure that we're constantly calling subroutines. So that's a good coding strategy. But what I would like to do is, as we go through this, show how the data that we track are going to update. So then I can go to VS Code and code it up. I always am going to want to represent my data with a matrix. And I always want to make sure I'm thinking about a tree. And how I'm representing that tree is as a collection of nodes. So we saw when we looked at the data set up for our trees previously, we said, well, there's a few different ways of doing that. One of the ways in which we could do that is to say the tree is a collection of nodes, but it's also a list of edges. And we saw that storing the edges is redundant. So the edges will just get stored within each node. And we will come back to that and mention it briefly here in a minute. But I also need some way of representing the current collection of clusters that we have in our data set. So the tree is going to start off as saying, I have a 4x4 matrix, and I'm going to wind up making 7 total nodes. In general, if I have an n by n matrix, I'm going to make 2n minus 1 nodes. And the reason why is, as I go up the tree, at any point in time, I reduce the size of the matrix by 1 row, and I add 1 node. So every time I add a node, it's because the matrix got 1 row smaller, and the final step is to make it a 1x1 matrix. So as a result, there are n minus 1 steps in this algorithm, and if I have n nodes at the bottom, n of my leaves, then I'm going to have n minus 1 nodes at the top, that are somewhere internal to the tree. So the first thing I'm going to do when it comes time to running the algorithm is to just create 2n minus 1 nodes. So that's going to represent the tree. All of the nodes down here at the bottom are going to get an age of 0. That will probably be the default anyway. Then the next thing I'm going to do is form an array or a list of that I'm going to call clusters that also refer to the leaf nodes. This is going to allow me at any point in time to understand, well, when I'm talking about the clusters that I currently have access to, what do they refer to? And the reason why is this matrix starts off with row 0 corresponding to node 0 and row 2 corresponding to node 2. But as we go through it, row 2 is not necessarily going to correspond to node 2. In fact, in the first step, we're going to join nodes 2 and 3 together. And row 2 is eventually going to point at an internal node. And so the clusters are going to represent how is it that data change over time. So how is it at any point in time I know which rows of the matrix correspond to which clusters over in the tree. I'll show you what I mean by that because it's going to allow us to track what the rows and columns actually represent. So at this first step, as I said, we know this was our example from before. We take our minimum element, we create a new node, and we assign it an age of 1. So I can easily assign this node an age of half of 2, which is 1. It will then have 2 children. So node 4 is going to have node 2 and node 3 as its children. And then we need to think about, well, how is it that this collection of clusters needs to update? And how does the matrix update? So we will do something a little bit different. Rather than trying to update the matrix in 1 step, I'm going to update it in 2 steps. The first step I'm going to do is to add a new row and column to the matrix corresponding to this new element. So now I'm going to have row and column 4. Where do these 3.5, 4.5 values come from? Well, I know that the distance from 0 to 4 should be the average of 0 to 2 and 0 to 3. Why? Because I joined together 2 and 3. So this 3.5 comes from that average. 4.5 comes from averaging 2 and 3 in this row as well. So the matrix actually gets a little bit bigger. And then I'm going to say, well, I joined 2 and 3 together. And so as a result, I'm going to get rid of the row and column corresponding to those elements. So I'm going to remove these unneeded rows and columns, and now I get to a 3x3 matrix. I'm also going to update my clusters that I have. And when I do that, I'm going to say, well, I want to add an element to them to refer to this new node that I created. So that's going to be one of my clusters. And now I no longer need to point these 2 clusters at the 2 leaves that I just created. So I'll remove those 2. How do I know to remove those? Well, the row and column values here, or the indices here, correspond to the row and column values that I initially identified. So I said here the minimum value is row equal to 2, column equal to 3. And that told me what to join together, which means these are the things that are going to go away. So when I make this new cluster, it's just simply going to refer to this node that I've created. And then these indices no longer need to refer to these nodes. As a result, I wind up with just 3 elements in this clusters list. The first 2 point to my original element. And then whatever the final element is going to point at this new node that I created. Then we just iterate these steps. So the idea is now we're thinking about everything in terms of data. I'm going to have a tree, I'm going to have a matrix, and I'm going to have a list that I'm calling clusters, where the list simply kind of refers to these nodes. And this list, as I said, connects this notion of what are the rows and columns of the matrix? Well, they tell you that these rows and columns refer to this. So row 0 refers to whatever clusters of 0 is. Row 1 corresponds to whatever clusters of 1 is. And row 2 corresponds to whatever clusters of 2 is, which is now pointing at node 4. I iterate again. So now I say minimum element of 3. And this minimum element of 3 says, okay, well, it's connecting 0 to 1. But we now know 0 to 1 over here doesn't necessarily mean node 0 and node 1. It does in this case, but what it really means is whatever clusters of 0 and clusters of 1 are referring to. So for example, if the minimum element happened to be at 1, 2, it's not, but if this had been our minimum, we wouldn't be joining 1 and 2 together. We would be joining whatever clusters of 1 refers to, and whatever clusters of 2 refers to, which is 4. So that's like our example before where I started to connect the nodes in this way. In this case, though, clusters of 0 and clusters of 1 actually do point at node 0 and node 1. And so when I find this minimum, I create a new node that's like labeled 5, assign it an age of 1.5, and then connect it to the two things that clusters of 0 and clusters of 1, which are these two nodes. Again, the matrix gets bigger and the clusters get bigger. So as those two things happen, the matrix needs to get bigger by saying, okay, what's the distance from this new cluster that I created combining 0 and 1 to this cluster that I had before? And when I do that, I'm going to say, well, I'm going to get a value of 4, which we saw because I'm going 0 to 2, and this is a 1-element cluster, and average 1 to 2, and that's also a 1-element cluster here. And so it's just going to be the average of 3.5 and 4.5, which is 4. So the matrix gets a little bit bigger. 3 now represents my new cluster that I've created. And then we're going to delete everything at row 0, row 1, column 0, and column 1, because that was the minimum element was at row 0 and column 1. We're now at a 2x2 matrix. We add a new element of clusters pointing at the new node that I created. We get rid of the two values in this list of node pointers that pointed at our previous nodes. And now we have a clusters array that points at two things. So what's nice about this is now the original leaf nodes have all disappeared. So they're no longer present in the matrix. When we say we have one element at row 0, column 1, and it's equal to 4, what does that mean? It means, well, the clusters list will refer to the two nodes that I care about. So clusters of 0 is going to point to 4. Clusters of 1 will point to node 5. And it's node 4 and node 5 that really represent this distance, because node 4 represents the cluster containing all the leaves beneath it, and node 5 contains all the leaves beneath it. And so really what this is a distance from this cluster to this cluster, and connecting this clusters array into those two nodes is really helpful in that regard. Now we'll see the final step. Well, what's the minimum element here? It's 4. What's half of that? It's 2. So my final node, which I was saving, is node 6. And node 6 here says its age is equal to 2, and I connect it to the two things that I just joined, which were clusters of 0 and clusters of 1. Those are going to be my two children. When I have that, I have a 1x1 matrix now, so when I add a row and column, it's just the distance from this thing to itself. So the matrix has one element. I add a new cluster that's going to point at this node that I just created, but I'm also going to get rid of the two things that it got joined to. So the clusters array gets bigger by an element, but then it gets smaller. And so when we remove those two things, we're down to just a single element. What does that point to? It always points at the root. This is worth appreciating. And this is the sort of thing that the first time I implemented this, I literally wrote it out by hand so I would understand how everything connects. And so I make sure I don't make a messy bug that's going to, result from a failure of understanding. Our idea then is to take this concept, and then I may come back and point out certain aspects of what we're working on. So we'll keep this example in mind, but we want to show how this idea of taking a matrix and producing a tree with UPGMA moves towards the level of code itself, while we're always going to have the idea of how this works in the back of our mind. And so let's do that. And I'll have an opportunity to ask some questions as we go. If we look at our UPGMA folder, we've got a few things here. We've got a little bit of starter code in main. We have some functions that we haven't written yet. So we're going to have our UPGMA function at the highest level that we're going to write to implement this function that we have seen. There's going to be some helpful things in this IOUtil function that will allow us to read from a file or write to a file. And we'll say more about that next time. The data that we are organizing is going to have the same organization that we saw in a previous code along, where we said, I'm going to think about a node as the node representing the edge relationships that I want. So the node will have an attribute for each of its children. Remember that we have this really weird string node or none equal none representation as the default value for a given child. But we're also going to have some things that are not as confusing. So we set the age as a default equal to 0.0, and whenever I create a new node, its string is going to get this default unlabeled string. We're going to have some methods too, which we'll write as we go through this. We're not going to need that for now. And then the final point would be, we also previously saw that I want to think about a tree as containing an attribute, which is a list of nodes. But if I'm representing an object and it only has one attribute, there's not really a need for doing this sort of thing that we saw up here, where I define a class and then I establish the attribute, which is a list of nodes. It just makes more sense for me to say I'm going to think about a tree as being defined by its collection of nodes. So we've seen this before when we worked with cellular automata. You may remember that I declared a game board as like a two-dimensional list of integers. Or I think we may even have started with Game of Life, where we worked with it as a two-dimensional list of Booleans. All that is as a type alias, is thinking of this as a synonym. Every time I see the word tree, I'm going to be thinking, well, I know it's a list of nodes, but I'm also conceptualizing it as a tree. Similarly, I'm also going to declare an alias called distance matrix that is simply a two-dimensional list of floats. So in the same way that we had a game board that's a two-dimensional list of integers to represent a cellular automaton, a distance matrix is just going to be a word that I use as a placeholder for what we're thinking of as going on behind the scenes, which is a two-dimensional list of floating point values representing these distances between different things. So our focus now is going to be on implementing this UPGMA algorithm. If we can make it, we can look at a lot of different data sets that we have. And I've given you quite a few fun different data sets. We have a collection of many dozen coronavirus viruses, SARS-CoV-2 viruses that come from patient samples. And as a result of this, we produced a distance matrix from this, where each value here is the distance between the spike proteins in 2 different patients' samples. And one of the things that's nice about that is we have the years associated with it. We also have some data sets associated with HIV subtypes. We have some involving some classic biological questions, like where does the giant panda belong in the evolutionary tree? And we have a mitochondrial haplogroup data set that will allow us to work with human samples where we've sampled their mitochondrial DNA, and this will hopefully show us the evidence of human migrations around the planet. So there's a lot of classic things that we could do. The idea is we're going to write one algorithm, and hopefully we're going to get a lot of different answers to real biological questions. So what we need to do, though, of course, is to implement UPGMA. And so that's where we're going to start. And we've also got like cytochrome proteins from a few different organisms. So I'll let you check out our data sets, and I'll probably expand on these data sets as we go. But at the end of the day, the idea is if we have good data and we have a reasonable approach for forming a distance matrix between them, as I said, we're going to talk about the algorithms for determining what are the distances between, what does it mean to say this is the distance for this gene between a giant panda and a raccoon, for example. That's a story for another day. But if we assume that we've done some analysis to give us that distance matrix, we can do it for that case, or we can do it for SARS-CoV-2, or we can do it for HIV. We can plug in whatever distance matrix we have, and it should give us a tree in any of those cases. For the moment, though, what we're going to do is all about just implementing UPGMA. So UPGMA is going to be plenty for our work right now, and it will start with a distance matrix. And we're also going to give it a collection of species names or taxa names that are associated with, what is it that each of these elements that's going to be one of our leaves in our tree, what are their names? And that's going to be very different in our data sets. In the case of the coronavirus data, it's going to be like a patient ID with a date that it was sampled from this patient. And these are all taken from the UK, where they had tons of public data. And for the case of, our giant panda data, the names of everything here are going to be the names of the organisms. So we'll have the Latin name, but these are American black bear, brown bear, polar bear, giant panda, and so on. So those are going to be the names of the species that we work with. And then when we produce the tree, we know what the tree is going to be. It's just going to be a collection of nodes. And each node may have 2 children representing the edge connections that we have. But at the highest level, I take the matrix, I take the names of the species that I want to label the leaves with, and I produce a tree. So this is not an easy algorithm, but as we saw at the level of pseudocode, it is going to be reasonably short. So the first thing I probably should do is actually just make sure that my data are okay. I'm going to be reading this in from a lot of different locations. And if that's the case, then one of the things that I might want to do is to say, what are the ways in which the data that I'm reading in might not be particularly valid? And I think there are a couple of things that come to my mind. There are many checks that we could do to validate our data. But there are a couple of things that would come to my mind. Number one would be, we probably should ensure that our distance matrix is valid. And there are a lot of ways in which we could do that. But one of the things that we definitely need to make sure is the case is that when the user tries to give us the data, it probably should be a square matrix. Okay, so that's what we've seen thus far. That's the only thing that really makes sense. It's an n by n matrix, so it should be a square. And I can write this function shortly, but then I should also think, well, that could be an issue, but we also could have some redundancy. So it could be the case that the number of rows in this thing, for example, is not equal to the number of species that we have. That would be bad. I want the distance matrix, if it's n by n, and it represents n species, I want those n species to be in this list of strings. So I also should have a function, and I'm going to call it assert same number of species, that takes, well, it takes my matrix and it takes my species names, and it ensures that those two things have the appropriate number of elements in them so that they're equal. If I know then at this point, so we now know that the matrix is square, and we also know that the number of rows is equal to the number of species. That's good, because one of the things that we otherwise might have started with was by saying, how many leaves do I have? The number of leaves I'm going to have is equal to the number of rows in my matrix. So I could have written it this way, and I could have written it this way. And if I had a discrepancy between those two things behind the scenes in the data, this could produce a problem for me. In this case, I'm not worried so much with that, because I know at this point in time, if I've made that assertion, I can type it this way or I can type it this way, and I know that I've already done the check to ensure that they're equal, which I'll of course write here in a function shortly. Then we're going to initialize our tree. So next we need to make a tree containing 2n minus 1 total nodes. And at every step of the way, I'm just going to continually apply writing a subroutine. So I'm going to say, I'm going to initialize the tree, and I'm going to give it the species names. Why? Because the leaves are going to get labeled with the species names. So I've got my tree at this point in time. I've not set any edges, of course, yet. And then the last thing I'm going to do is I'm going to recall that when we looked at how we're thinking about moving towards the implementation, there's one other thing that I want to set, which is to say I've got my clusters, and if I've got my clusters, well, what do they get initialized to? They get initialized to essentially just refer to all of the elements of the tree that correspond to leaves. So in this case, num leaves is equal to 4. And I'm looking at the first 4 nodes of the tree. So clusters of 0 will point at nodes of 0. Clusters of 1 will point at the nodes of 1, and so on, up for all of the leaves. And so if I want to take that idea and represent it in code, well, I would say clusters here is then equal to, look at the tree, because the tree is going to just be a list of nodes. Remember, when I'm thinking about my data types, I just think about a tree as constituting a list of nodes. I have this alias there. And for that reason, the clusters are initially going to refer to the first num leaves nodes in the tree. So if I've made the tree, then clusters is going to be just t up to num leaves. So this will be the collection of nodes having indices between 0 and not num leaves, but num leaves minus 1. Now I have a question for you, which is this going to be a problem? What might cause a statement like this to produce a problem? And if you don't know, that's okay, because we're going to come back to it. For now, this certainly seems innocuous, right? I don't know. It's honest. Empty array? I don't know if I would worry about it being empty. Because I'm going to have a function that's going to say, at this point in time, the tree is going to have 2n minus 1 nodes in it. So t is just a list of nodes. And we know num leaves is going to be a valid value. So it's really just, this is a collection. This is just a list of n things. So let's hold on to that thought. So I've got the tree. It's not going to have any edges. And the clusters refers to this first num leaves nodes. And then we're going to perform the engine of UPGMA with n minus 1 total steps. Why? In every step, we're going to make one new node, and the size of the matrix is going to get smaller by 1 until we wind up with just one element. So we're going to say for, and before I even do that, I'm going to say eventually return the tree. So we think about everything in terms of what is it that is our input? It's a distance matrix and species name. What is it that we're returning? It's t. So at the end of the day, I'm going to return the tree. And I can work on visualizing the tree. I can write it to a file. I can do all that fun stuff much later. But for now, the function at the end is just going to return the tree object that I care about. So what is left then is I've made the data. Eventually I'm going to return the tree. And in the meantime, I want to range over all of the steps that I perform. And I want to do all of the steps of UPGMA. So at the highest level, I'll say we want to range over all of the internal nodes. Okay. So range over all the internal nodes and perform one step. So the internal nodes start at index num leaves, and they're going to go to up to but not including 2 times num leaves minus 1. We say, why is that the case? Well, we know from before, if I have n rows in my matrix, I'm going to make n minus 1 internal nodes, 1 for each step of the algorithm. So at the end, I'm going to have 2n minus 1 total things. As I go through this, I'm going to go look back at my example. So what is it that happens each time? I find the minimum element. I join the new node that I have, which at this point in time is just going to be the current node. I'm going to say its left child is here and its right child is there. So child 1 and child 2. It's easy to think I'm joining this to node 2 and node 3, but remember that the matrix corresponds to the tree because of the clusters. So I'm going to be joining this node to clusters of 2 and clusters of 3. Then I'm going to set the age of this equal to 1/2 of the value that I have, of course. So the age here is going to be equal to 1. Then I add a row and column to the matrix and make it smaller. So I delete a row and column. Then I add an element to the clusters that's going to refer to this new node that I created. And then I delete 2 elements from the clusters so it gets smaller. So all of those steps need to appear in our code. And when we do this, therefore, the first thing I'm going to do is say, let's write out some comments. The steps are find the minimum element of the matrix. Then set the age of the current node. Connect the current node into its children. Add a row and column to the matrix. Delete the old rows and columns that are no longer needed. Create a new cluster referring to the new node that we created. And delete the 2 clusters that we joined together. If we tried to do all of this without any subroutines, our chances of understanding this would be essentially 0. And if you go and you ask AI, to make good code for you. It doesn't try to do something like that. It's always going to use best coding practices and separate everything out into these nice modular functions. But this UPGMA algorithm is a great example of modularity taken to the extreme. And we're now moving towards more complex applications. And the functions themselves don't necessarily need to get huge, but they do need to call for help wherever they can. So by calling for help, the first thing I'm going to do is to say, I want to have a function that's going to find my minimum element in the matrix. And it's going to tell me what's the row index and column index, where it comes from, and then what's the min value. So it'll return these three things. And I'm going to say it's find minimum element of the matrix. Then once I've done that, I'm going to set the age of the current node. Now the current node, every time we go through this, I want you to notice, well, P is going to range between num leaves and 2 times num leaves minus 1. So if we look at my matrix, in the first step, the current node is 4. In the second step, it's going to be 5. In the third step, it's going to be 6, right? And so in general, I'm starting my ranging at number of leaves. So in this case, number of leaves was 4. So I start P at num leaves. And then in each step, P is going to get increased by 1. So the current node is actually always just going to be T of P. So T of P is going to start off as T of num leaves, and it's going to be T of num leaves plus 1, and so on up until I get to the root. So the current node is always just T of P. And its age is going to get set to be equal to half of something, and the half of something I care about is this minimum value that I get as a result of finding the minimum element in the matrix. Now is for the hardest part in this algorithm, and I'll be very impressed if you know when I set T of P dot child 1, it needs to be equal to something, and T of P dot child 2 also needs to be equal to something. Here's where we're adding what we're thinking about as the edge connections in our tree by saying we have a node, and our node is going to set child 1 and child 2 to refer to 2 other nodes. But then the question becomes, what are those 2 nodes? If you happen to know, I'll be impressed. One shroot buck to the chat, if they can help us out. And I will go back and say, is there a pattern? We'll look at the example that we saw before. Here is me. Here is T of 4 for this example that we have before. So it's connected to these 2 children. Then I add a new node, T of 5. And it's connected to these 2 children. And then we have another node, T of 6, and it's connected here and here. So it's easy to say, well, it has to involve T in some way. T of 6 is connected to what? And if you try to say what T of row and T of column, that doesn't make sense, because in this case you can see that it's connected to nodes 4 and node 5. But the one thing that's always shared is here's where we get to use clusters. So when node 4 comes in, notice we connect row index is equal to 2 and the column index is equal to 3. So that's where we found our minimum. 2 and 3, so when we find the minimum element, it's going to say we have minimum element of 2 at row index 2 and at column index 3. This is clusters of row and clusters of column. These refer to the two children that we connect it to. Let's see if that pattern persists. So now when I add a new node, T of 5, it also has a min value of 3 at row equals 0, column equal to 1. And notice it's connecting to clusters of 0 and clusters of 1. Then when we add our final node, which is T of 6, at that point in time, the minimum element is at row 0, column 1. And notice we're connecting 6 into clusters of 0, which is node 4, and clusters of 1, which is node 5. So the pattern is always preserved, and this is what the clusters array is so nice for, that at every point in time, the first child is going to be clusters of row. And remember, this is a node. Okay, we know it is a node because we said the clusters is just a list of nodes. Okay, what is the tree? It's a list of nodes. What are the clusters? They're just a list of nodes. And the second child points at clusters of col. Now we carry on and we say the matrix needs to get bigger. So the matrix gets bigger by saying matrix is equal to add a row and column. And in this particular case, we're going to say, well, I need to know matrix, row, column, and we need to know two other things too. I need to know the cluster sizes of the two things. And the reason why is when I add these values, remember that this is where that weird averaging is going to take place. So when I go at each point of this algorithm, when I add a row and column, why is this 3.5 and 4.5? It's because I compute this average of the distance from 0 to 4, or excuse me, the distance from 0 to 2 and the distance from 0 to 3. So these are the two things that I join together. And as a result, when I add the row and column, I need to know how many things are in each of these clusters. Now, in this case, it's equal to 1, but that becomes a lot trickier when I have this final case and I've got this new value equal to 4, and it connects to each of these two things. And when I form this weighted average, I want to be able to know that there's two things over here and there's two things over here. So as a result of this, I need to know the cluster sizes. And the cluster sizes will become really important when I want to perform this weighted average. And here's where I'm going to say the cluster size of the first child is to look at each child and count the number of leaves beneath it. If we look at our picture again, and I say, how many elements are in this cluster? The number of elements in this cluster is equal to 2. Why? Well, it's the number of leaves beneath me. Why is the number of elements in this cluster equal to 2? It's the number of leaves beneath me. If I look at a simpler example, like here, if I were saying, what's the number of elements in this cluster? It's just 1, because there's just one leaf in the tree beneath me. So there might be 1,000 leaves beneath me. There might be one leaf in my tree. But in either case, I'm going to set the two cluster sizes equal to the result from counting the number of leaves. Those are going to be helpful. And the question becomes, how do I write such a function? It is going to be a node method. So when we see this, it might look a little scary. This just says t of p.child1, that's a node. And this is what we saw in our previous code along, where we said we can write a method where we use this dot to indicate, the class that we have before the dot. And then we say dot the name of the function, which in this case is going to be count leaves. So we'll write that function too. And then I want to remove old rows and columns that are no longer needed. So in this particular case, I'm going to say matrix is equal to delete a row and column of matrix row and col. So those are the two elements that I want to get rid of. So when I go back and look, and in this particular case, so I've added the row and column, I'm going to remember the minimum element here was equal to 3 when row was 0 and column was 1. So those are the two clusters that I'm joining together. As I've seen here, I've joined them into this node. And when I do that, eventually these two clusters are just going to go away. So after I add this row and column, I no longer need the rows and columns corresponding to 0 and 1, and I no longer need the clusters corresponding to 0 and 1. So after I add this new cluster that points at this node that I added, I no longer need clusters of 0 or clusters of 1 either. So I remove both of these by saying they get bigger, and then I remove the row and column indices here. I'm going to create a new cluster referring to the new node. That sounds hard. All I'm doing is taking the clusters and appending the node that I've created, which is TFP. And then I'll have a subroutine that's going to be called delete clusters. And it's going to take my clusters and it's going to take a row and column. And it's going to get rid of the clusters at this index and at this index. At the end of this process, we're going to return the tree. So that is our highest level function. And once we have it, then we can go through and start writing subroutines. And that's where, it takes a lot of work to get to code like this. That is this modular, right? It's not a very long function. It calls 1, 2, 3, 4, 5, 6, 7, 8 subroutines. But it's doing so in a very coordinated fashion where we understood the algorithm perfectly before we ever wrote any code. Of course, I should write my assertion functions. Those are going to be straightforward to write. So the idea of asserting the square matrix is to ensure that the matrix actually is square. So the first thing maybe we could do would be to say, look, if we could say the number of rows is equal to the length of the matrix. And if for some reason, like that's equal to 0, that would be bad. So I'm going to raise a value error and say matrix, empty matrix given. So that should be an error. But if I'm otherwise, what I want to do is I want to ensure that that matrix actually is square. To ensure that it's square, the idea is range over all the rows, and each row should have length equal to the number of rows. So each row should have a certain number of elements that we think of as the number of columns in the matrix. But it's possible to have a list where not every row has equal length. So I can verify that it is indeed square if I say, well, 4, in this case, let's say I and range over the number of rows. And if it's ever the case that the length of the matrix at row I is not equal to number of rows, we can say non-square matrix given. Okay. And if we survive all this, we don't need to take any action. We're fine. We know that the matrix is square. So if we make it here, we know the matrix is square. We also have this function to assert that the number of rows in that matrix, after we know that it's square, is equal to the number of species names that we have. So we take two arguments, a matrix and our list of species names, and we want to ensure that those two things match. This is an easy thing to check. It's just to say if the length of the matrix is not equal to the length of the species names, well, we want to produce an error there. So number of rows in the matrix is not equal to number of species. So if we have this, we know that our data are good. And now it's just a matter of saying, well, let's go through and write each of the functions that we need to. So we could perhaps even go in order. We could start with initialize tree. So initialize tree is going to say we've got a collection of species names. We want to make, if this has n items in it, we want to make 2n minus 1 total nodes. And we want to label the leaves of that tree with the species names that we have. So when we have our function, initialize tree, it takes those species names and it produces a tree. Let's set num leaves is equal to the length of our species names. That could be useful. And then I'm going to have a tree. So it's just an empty list, but I could be a little nicer to me, the user, and say, I know it's a tree. And a tree is just a list of nodes. Okay? So I declare my empty tree. And then let's give the tree 2 times n minus 1, not nodal, total nodes. So I'll say for I in the range over from 0 up to 2n minus 1. And for every one of these elements, I want to create a new node. And that new node is just going to be a node, this will get default age equal to 0. And I'll say, let's say t.append this new node that I made. And then I want to give it a label too. So I will say, if I is less than the number of leaves, well, in that case, the label that this thing is going to get as its attribute is just species name of I. And otherwise, so in the other case, well, we're at an internal node, so we're just going to label it with I. And I'll give something a little bit fancier. I'll say t of i's label, in this case, is just equal to like an f string where I say ancestor species, and I'll put I in braces. At the end of this process, I've got my tree. So at this point, I'm going to return tree, t. So I made my nodes. I've not set any edges. All the nodes are going to have the ages that I care about. And they're going to also get the label that we care about. The ages are all going to start at 0 because if I'm at an internal node, I've set its label already, but I don't know what to set its age at because that's going to get set as we go. Now we return to where we were in UPGMA. And I want you to remember that we've initialized the tree. So the tree has 2n minus 1 nodes in it. And the first n of those nodes are going to be my clusters. And our question was, is this okay? Another way of putting it is, should this make new nodes? And to get at what I mean there, I'm going to say, why don't we go into main? And I want you to consider the following example. So say that we have a list of integers. That list of integers is a equal to, let's give it some values, 10, 20, 30, and 40. And then I'm going to set b equal to a sublist of that. It's going to get, it probably feels at this point maybe like a huge relief to go back and do something as simple as sublisting. So I'm going to set b equal to the first 2 elements of a. And then I can print b, and we'll see that. So if I go into a terminal, I'm going to navigate into src/UPGMA where this code is, and then I'll run it. So I see b is indeed the values 10 and 20. And so far, so good. But then I'm going to do one more thing. I'm going to set b of 0, the initial element of b, to be equal to 99. And then I'm going to print a. And the question becomes, what gets printed? There are really only two possibilities. We know that b has two elements in it, corresponding to these first two elements. We know that a has four elements in it, corresponding to these elements. But the question becomes, well, which of two possibilities are there? Is it the case that a is going to be 10, 20, 30, 40, as was initially the case? Or when we set this the initial value of b, does it also set the initial value of a? So the question is, what is printed? Is it 10, 20, 30, 40, or is it 99, 20, 30, 40? And I put that as a poll. So let's see what the chat thinks. Chat thinks 71%, so the winning vote is for 99, 20, 30, 40. When I run it, I see that, well, that's not exactly what happened. So when I set b equal to a colon 2, what we're working with here is a duplicated form of the data. So we have two different lists. Even though I looked at 10 and 20 here, I have created a copy of it. And we can see that by the fact that if I print b, you'll see that b is indeed 99 and 20. So these can't refer to the same data because they have different values. All right. What about nodes? So we get to do a little bit of practice with declaring an instance of a user-defined class. So we're going to be able to say, well, let's make a equal to another list, except now this list is going to contain two nodes in it. It's going to have one node and another node. And let's give it a little bit more than just two blank nodes. Let's give it a label. So the first node is going to have axolotl as the label. And we can make the next one pretty memorable too by saying it's going to have the label of blobfish. And I want to make sure that I'm getting a little bit of a warning here because I have the node declared in data types. So I want to make sure that I then say, from data types, import my node class that I have. Now when I save it, I'll see that I no longer have that yellow underline. And then the question becomes, well, let's do the same thing. So let's set b equal to, let's say the first element of a. So this is a minimal example here. And what I would like to do is to say, let's print b of 0.label. So when I do that, you'll see everything is fine here. It's going to print axolotl. Why? Because a is a list of two nodes. B refers to the sublist containing just the first element. And so when I print b of 0's label, I'll see that get printed. Let's change the label. So instead, maybe I change the label of that node. to be capybara. And then we're going to print not b of 0 dot label, but a of 0 dot label. Okay. So b is really just a list containing only this node. And after I make that list, I'm going to say, all right, change the label of the one element of B to our capybara. And then the question is, well, does the label of A change? So we want to know. And let's see if the chat can redeem itself. I'll ask you, what gets printed? There's only two possibilities. It could be axolotl or it could be capybara. You'll always choose capybara. I can't go against that logic. It's perfectly reasonable. I don't know if it matches what Python's implementation is going to be. Exercise your democratic right to vote. What do we think? Will B's label be? B's label is definitely capybara at this point in time. What's A's label going to be? Okay. Once again, completely divided. I want the chat to win one, because since I've started doing these polls, I don't think that there's been like a majority vote that's been right. So you couldn't win this one because it was 50-50. So let's see. All right, when I run it, we see capybara. Now maybe it's because capybara always wins. Okay, but we could also name it chicken, and that's going to win too. All right. So the idea is here, we have two differing behaviors. In the case where A was a list of integers, and then I said, well, just take this sublist. It works with a duplicated form of the data because we can see this. I change an element of B, and it doesn't change A. So when we printed, so for example, A is this, and B is this, then when we print it, A is 10, 20, 30, 40, and B is 99, 20. So we see there's two very different copies of the data. But now, I initialized A to be axolotl and blobfish. I set B equal to the first element here. I changed B of 0's label. And notice that it has changed. The first label of A is A of 0 dot label. That's chicken. Okay. So, in particular, I could get it another way if I just print A. And we see, I wrote it the other way for a reason. We still see that it has two elements in it, the chicken and the blobfish. So, A still has two elements, but we've somehow accessed the label of that first element of A through B. And so that's completely different from what we saw with integers. The question then is, what is the difference here? What's the difference between the first case that we saw with integers and the second case that we saw with nodes? Where in one case we got a copy of the data, and the other we're able to actually change it. AKB said the magic word, which answers all of our questions, right? So at this point, we know we could just have a bot that just constantly says the word mutability. I think I touched on this very briefly in another class, but the notion of looking at specific, like what happens when you take a sub-list of a collection of mutable things versus a collection of immutable things, what we see is in the case of mutable objects, so when we take a sub-list, like it's called a slice, of a collection of mutable objects, we get access to those things. Okay, and so you can change the original list. But even if we've seen something similar to this, we now actually have an understanding maybe of what actually is happening. So yeah, we know that the behavior is different, but then the point is, well, actually the behavior is the same, but what we see as the end result is different in these two cases. When we set this, what happens is we still get copies, but we get copies of references to the data in A. So it's as if the analogy I've always tried to give students in a case like this is deep in the bowels of the computer. It's like a storage facility. And so you have places where things get stored. So your node that started off with the label axolotl lives somewhere in a storage locker. When you set b equal to a:1, what this does is it does create a copy of something. But what it creates a copy of is essentially, like in the case of integers, it creates copies of your integers. It says, oh, you want b equal a to 2? Okay, well, I'm going to go in and I'm going to duplicate 10 and 20. They're just integers. But what gets copied in this particular case is not the node. What gets copied is the reference to the node. So we start off with 2 node references, which is what constitutes A. And when I say b equal to a:1, it's as if what you duplicated is the key that unlocks the door. But if I make a copy of the key, I'm thinking of that in this case as a copy of the reference to the data. Even with a copied key, I can go in and unlock the facility and change. I'm subbing out an axolotl for a chicken, which is what this has done. So B has access to a copy of the underlying data, but the underlying data was not the node itself. It was a reference to the data in A. So that's an important thing to keep in mind. And it's a good thing because what it means is that when I look back at functions, the answer here is that it is not. It makes copies of the keys to the locker that contains the leaves of the tree. And that makes sense. That's good. So Python behaves nicely here, but it's important that we understand, like, there is a difference here if T is a list of nodes and if T is a list of integers. Because T is a list of mutable things, I can refer to these nodes in one of 2 ways. I can refer to them as the elements of T, so the first num leaves elements of T, or I could think about them as the elements of clusters. And that's what I wanted you to think about. Go back to like our original picture. When we think about it this way, I've got a tree, and the tree has 7 nodes in it, but the first 4 nodes are the things that I care about as the leaves. But when I create the clusters, you'll notice I have these arrows. So the idea is I want you to think about clusters of 0 contains a reference. It's like the key to the storage facility where this node of 0 lives. And the same for all these other elements. So when I set the clusters, I'm really just creating references to each of these 4 nodes. And that's what I want you to think about with the arrows. In a lot of languages, this is handled in a way that is a little bit trickier to understand at first with something called pointers. But that in the long run is way easier to understand. In Python, you just always have to remember that if you create a sublist and the underlying things are mutable, then you're getting references instead of duplicating underlying data. Now we can come back to our engine of UPGMA, and we can work on each of the subroutines that we have remaining. So before I do that, I'll point out we see the same thing happen that we had here. We have the same thing happen here. Okay. So when we look at this statement and see tfp.child1 is equal to clusters of row, well, this type of assignment with mutable things, we've seen this before. So this means update child1 of the current node to be the reference to the node in clusters of row. And that's good, right? We are not saying make a new node. Okay. So that I think we have seen before, which is when I have one node or one object and I set it equal to another object. This is what we talked about when we saw shallow and deep copy, right? This does not make a copy of the node that's contained at clusters of row. That would be bad. What it does is it says, oh, whatever this refers to, well, tp.child1 refers to it now too. So go in and look at what the reference is, make a copy of the key, and hand this key off to tp.child1. And that's a good thing. So that's what we want it to be. Now we can find the minimum element. And we don't have so many more subroutines to write. So I should write my find min element. We'll need to look at this method. And we'll need to look at add row column and our delete functions. So we have a little bit more code to write before we wrap up. But the first function I'll look at is, I think I've got these in alphabetical order. Find minimum element. So this minimum element here is going to look at a distance matrix and identify three things: the row and column index, as well as the value itself, where we get this minimum element. So maybe the first thing that I do is, I don't know, make sure that the matrix has at least 2 rows in it. That wouldn't make a whole lot of sense. Or if the length of this first row, if that were equal to 1, either of these would be bad. So raise the value error and say, matrix isn't large enough. Because what I would like to do if I'm looking at a matrix and I'm saying, what's the smallest element? Well, I might set a row equal to 0, a column equal to 1, and say the minimum value is what happens when I look in the matrix at that row and that column. So if I go back and I look at, for an example, matrix, the matrix is going to be symmetric. So if I look at my original matrix here, this value will be equal to this value, and this 3 is equal to this 3. So I'm really just going to range over the matrix by starting a value here. And I know that value exists because I know that there's multiple rows in it. And I know also that I already checked that the length of the initial row has to be at least 1. Okay, so far so good. And I know that that element exists. And now the question is, how do I perform my ranging? So I need to scan over all of the values in this table. But then a question for you, here's an opportunity for you to think about this, is what values do I scan over? How do I actually perform this ranging? So when I bring this idea and went too far there. When I bring this idea and I take it back over to the level of code, I want to range over the values of the matrix. And anytime I find a smaller value, I update these values. At the end of this process, I want to return the row, the column, and the min value that I've found over all of those possibilities. But then how do I do this ranging? What do I range over? That's the question. So we're nested for loop. That's good. Good. But there's some votes. So one of the things we could do is I could say for, I don't know, R in range over the number of rows, which is the length of the matrix. And then for C in range over the length of matrix of R. And then if I ever encounter a matrix value that is smaller than my current min value element, then I'll update the three things. And I can update all these three things with just one line. It's not something that we've seen a whole lot of, but it's a natural place for me to say, let's update three things all at once. And I'm going to update them to the current row and column index that I'm at, as well as, well, the current matrix value. So that would be fine. But that's suffering from one little thing. So nested for loop is good, but this has a problem. And what's the problem that we would have here? There's going to be a bug here. Or it says the zeros. Good. Excellent. So if we look at our matrix, we need to be careful. Because if I range over this every value of this matrix, the min values in a distance matrix are going to be 0 because the main diagonal is going to be 0. And all these values off the diagonal are not going to be 0. So we need to make sure that we're aware of that. And as a result, I only need to range over, say, like the upper right part or the lower left part. And it doesn't matter which direction you go in. So we could go above the main diagonal, below the main diagonal. I would say it probably is important for the sanity of the user that you're consistent in how you do it. So we're always going to look in upper right. But as long as you pick one, that's going to be okay. So when we look at our code, we actually have this in the doc string. We're going to demand that the column index is bigger than the row, which means that if we look at our matrix, the column indices are bigger than the row when we're in this upper right triangle. And then it just becomes a question of how to perform the ranging. So when we look at find min element, I'm not going to range over all possible column values. I want to start at r plus 1. So if I start at r, that would be bad, because then I'm going to get a 0 value. That's when c is equal to r, I'm on the main diagonal. But if I start at 1, then we're going to be okay. This, though, I saw, good job, Iris, you got this one. All right. But then this, though, also has a little issue. And this issue is more minor. This issue says, well, if I'm looking at the upper right part of my matrix, then I don't actually ever need to consider the final row. So the ranging over the rows doesn't actually need to go up to the length of matrix. It can go up to length of matrix minus 1. And now, this line is going to stay the same. This line stays the same. But I'm just ensuring that I'm ranging the column value over everything appropriate. This indicates there's a nice exercise here, which I can leave to you. So a nice exercise would be to say, write a function that asserts that matrix is a distance matrix right? We're making a strong assumption here. So what does it mean for something to be a distance matrix? It should have non-negative values. It should be symmetric across the main diagonal. And then diagonal. And then it should also have the triangle inequality. Okay. And that means that if I have I, j, and k for any possible choice of these three values, the distance from like I to j has to be smaller or less than or equal to the distance if I go from I to k and then go from k to j. All right. So you might imagine we could have a function that asserts this so that anytime we generate, a matrix from biological data, we make sure that it actually is a distance matrix. That's a little much for what we want to do. We want to implement UPGMA assuming that our data are okay. And so I'll leave that to you if that's something that you want to do. For now, though, I've got my function, and we're running out of subroutines to implement. We have another function that we need to write called add row and column. Where does that come from? That comes from when we grow the data. So when we go from an n by n matrix to an n minus 1 by n minus 1, we have this brief step, right, where we actually add a row and column corresponding to the new cluster that I've created. And here is where the trickiest part of the algorithm from the perspective of needing to perform this weighted average comes in. So when we write this add row and column function, here's where, this uses the idea that if we are merging clusters with sizes S1 and S2, then the distance from, let's say, the new cluster to cluster K is given by this formula, S1 times the distance from K to row. And here, corresponding to indices row and col of the matrix. So we take the distance from K to row, and we weight it by S1, which is the cluster size. And then here's where we saw, we need to make sure that we're performing this average as a weighted average. So I'm going to take the size of the second cluster and say, what's the distance from that cluster to K? And then I'm going to divide all this by the size of the two clusters. Okay. So I'm just writing this down as a guide to myself because I'm eventually going to use this. And here's an opportunity for me to just appreciate that that's the formula. Then I can just focus on the implementation. So I need to be careful with the indexing. That's kind of the general idea of this function. And the first thing I'm going to say is, well, let's set number of rows equal to the length of my matrix. And when I expand this, I'm not going to try and think about, well, I've got an n by n and I need to go to n plus 1 by n plus 1. I'm just going to, make a new row, and then I'll fill in the other values. So I'm going to set new row to be equal to just a bunch of zeros. And the new row needs to be one element longer than all of the rows currently are. So if we have this matrix and we're making a new row, the new row here is going to have an extra element down here with the 0. So my new row is going to say it's going to have a bunch of zeros, but how many values are there? Well, it's number of rows plus 1. And we'll worry about the extra column values later. That's something I can handle later. But for now, I'm going to say, let's set these values. So I'm going to have an R that ranges over all the values that I care about. And I'm going to say range over all the values in the new row. There's one value that I actually don't need to set. So the final element here is already set to 0. So when I make this new row and I come here, this value here is always going to be 0. So when I range over these values to set them, well, I don't need to set this value. So as a result, minor little point, I'm going to range over not the length of the new row, but length of the new row minus 1. And then I'm going to set all these values according to the formula that we have. except there are some values that I don't care about. I don't need to set, well, new row of row or new row of col. Those are the indices where, when I went from here to here, row is 2, column is 3. I'm going to eventually be getting rid of all this stuff. And so if I'm getting rid of that, when we go here, those are the rows and columns I'm going to delete. I don't need to worry about setting any of these values. So I'm only going to set the values if, the current index, which is R, is not equal to either of these things. So I'll make that test. I'll say, if it's the case that R is not equal to the row and R is not equal to the column, great. In that case, I'll set it. And here's where we get to apply this tricky formula to say new row of R is equal to the formula. Okay. And at this point in time, this is kind of, I guess, this is my K. Okay. So when I say the distance here to this particular cluster is equal to this weighted average, so I know I'm going to divide by the sum of the cluster sizes. So that's important. And then this formula says, well, how many things are there in cluster 1? So that's going to get multiplied by something. How many cluster elements are there in cluster 2? That's going to get multiplied by something. And then I divide by this. So again, as is often the case in this class, I am literally just trying to delay the hard stuff for as long as I can. I know I've got new row of R, then I need to set it because I'm ranging over R. And I know that cluster size 1 and cluster size 2 are going to factor into this weighted average in this way. And then I just have to make sure I get the question marks right? So you might even pause for a second and think, like, what are these question marks, right? How is it that I tie this to what we were looking at with this weighted average that I have before? What is this? And what is this? Yes, I think you're asking a question about, should this be this? But notice the new row has length equal to num rows plus 1 as is. So I could do this in one of two ways. I could say I'm ranging over num rows. Okay, that might make it clearer. But really it's that I don't need to go to the very end of new row, which means normally if I range over everything in this new row, I do that. But I don't need to set the last value. So then the question is, what goes in the question marks? And if we look at our example, well, when we look at new row of 0, how does that value get 3.5? When we look at the grayed out things, it's because the distance from 0 to 2 is 4, and the distance from 0 to 3 is 3. So we take the average of these two distances. So we say, well, 0 is just R, okay? That's where we are in new row. So when I go here, R is equal to 1. And I would take the distance from 1 to 2 and 3. And now we see the pattern, right? So we see R is one of the values that I'm going to take the distance of. And the other two are, well, it's the distance from R to row and the distance from R to column. So this is going to correspond to cluster 1. This is going to be corresponding to cluster 2. And as a result, I can set this to say, well, why don't we say this is just the matrix value of R to row, and this thing over here is the matrix value of R to col. And now I've made all these data. Now, I want to be careful because at this point in time, I've just made the row. So I need to do two things. Append this row to the matrix and add the extra values with symmetry. So I can append the new row by saying matrix.append new row. But at this point in time, I've got this weirdly shaped matrix, right? If I look back at my example, when I go from here to here, I've set all of these values in the new row and I've appended it to the matrix, but I'm missing all of these values. So I need an extra little step where I'm going to get to use the fact that I can just say symmetry. So I'm going to append this 3.5 to the end of row 0. I'm going to append this 4.5 to the end of row 1, and so on. So I will say, now set the missing values due to symmetry. And I'll say I don't need to set the bottom right. So that one's get set for free. And I'll say let's range now over the number of rows. This is nice and clever because what's number of rows? That's the length of the matrix. So num rows is our original n. I never actually changed it. And now I'll be able to say matrix of R dot append. And at this point in time, what am I appending? I'm appending the corresponding value of the new row. So that's the value that I care about. So the other way I could do this is to go in and access matrix of num rows of R. So that works too. But for my taste, I think I can get there a little bit faster and it makes a little bit more sense. If I say, really what I'm going through is I'm saying in row R, I'm just looking at the value that I set in this new row and accessing it. Of course, there's one final thing to do, which is to return that matrix. Thinking about everything in terms of subroutines makes this super easy. And now we're down to just a couple things to do. We've got, if we look at UPGMA, we've got our count leaves. So we've got these functions to write. And we also need to clean up the matrix and the clusters. So we can add a row and call to the matrix. Remember, I'm just appending T of P to the end of the clusters. So I don't have to add a cluster. But I should handle each of these things. And I want you to remember, didn't seem important, but remember that when I wrote add row call, I always assume that column is bigger than row, right? In other words, I'm in the top right of my matrix. So if I'm making that assumption, then I can state that it means column is bigger than row. So let's look at delete clusters, and what I'm going to say is I want to remove the elements of clusters at indices row and col, which means this isn't hard. I'm going to delete, I have a built-in delete function, thank you Python, clusters of row. I'm going to delete clusters of col, and then I'm going to return clusters. Super easy. Also, wrong. Now the question is, who has the answer to tell me, what did I do wrong here? What did we mess up? Seems straightforward. Where's the bug? The terrible bug here. So because of how we define clusters, the row and column indices that we get from the matrix do correspond to what we want to get rid of in the clusters. That's the genius of the approach, right? That after this point where I said, well, this is row index 0 and column index 3, the clusters point at these two nodes. So this is row index 2 and column index 3. So I'm just going to take those two indices. And those are the very two things that we want to get rid of. And that's always the case. So it's the case here. And then in the next step, so when I say the minimum element is at 0, 1, well, clusters of 0 and clusters of 1 are going to be what we delete. Okay, and then in the final step, we've got this particular case, and it's 0, 1 again, but clusters of 0, clusters of 1 correspond to the two things that we're getting rid of. So we append a final cluster that points at the root, and then we get rid of those two other things. So those are the correct answers in terms of the indices that we want to remove. But there's a problem here. So say hypothetically, let's look at main. Iris says delete call first. And I wonder why we didn't get that answer like 2 minutes ago, because we could have wrapped it up a little bit faster. But let's say, for example, we have C, okay? And it's a list, and it's 1, 2, 3, 4, 5. And I'm going to delete, well, let's get rid of C of 1. And I want to get rid of C of 3. So this is C of 1, and this is C of 3. Say I don't like even numbers. And then I print C is C. Now when I run that, you hope that you're going to see 1, 3, 5. But what you actually see is 1, 3, 4. And the reason why is C is now 1, 3, 4, 5. You were trying to like eject the people from seats 1 and 3 of the movie theater. But the problem was in this row, when you got rid of this person, everybody else kind of shifted down. So all these elements moved over 1, and as a result, when you delete C of 3, you thought you were deleting the 4, but the 4 already moved over, so C of 3 is this. And I'll add one more value so you see. When we run this, C is 1, 3, 4, 6. Okay, so you removed the 5, not the 4, and that's a problem. So the issue is everything shifts over one element when you delete something. That makes a whole lot of sense. But when you thought you were deleting C of 3, you did delete C of 3, but it was in the modified data set. So it wasn't in the original thing. You thought you were getting rid of the 4, but you actually got rid of the 5. So we need to keep this in mind. It's a minor point, but if we don't ensure that we delete, always delete the higher index first. Otherwise, everything's going to shift over. So this is all fixable by remembering we specified that column is bigger than row for a reason. And now we understand because column was bigger than row, because I grabbed that min value from that top right of the matrix. You probably thought at the time no big deal, but it's actually really important now because it means that I know that column is bigger than row. So when I delete them, we can make sure that we delete the higher index first. Okay, So that's where our bug was, and we're going to return clusters. It also means that I can do the same thing with delete row column of the matrix. So I have two indices that I care about. I'm going to delete the rows at those indices, and I'm going to delete the columns at those indices too. So to implement this, it's just the two-dimensional version. Remember, column is bigger than row. Kind of important. So in this particular case, first, delete the two rows. Okay. So when we look at our example, right, here is one particular example. I add a row and column, but then I was looking at row equal to 0 and column equal to 1 here. So I'm going to remove the row and the column with indices 0 and 1. So in general, I'm removing the row and the column with indices row and col. So I'll get rid of the rows first, and I'll say, delete matrix of col, delete matrix of row. Col is bigger than row, so I want to delete it first. Then what I want to do is I want to remove, there's n minus 2 rows left. And what I want to do is range over all of these rows and remove the elements at indices row and col. Col first. Why? Because col is bigger than row. So I want to say for r in range over, and I want to be careful here, right? So I say, well, it's n minus 2, but I don't need to think about it as n minus 2 if I just set num rows equal to the length of the matrix at this point. This is now n minus 2. Okay, so really, I'm just going to range over that number of rows. And when I perform that ranging, what did I do? I tried to hit a colon. When I perform that ranging, I'm going to say delete matrix of R. And it's so tempting to put row, but remember col is bigger, so we're going to say col. And then I'm going to delete n matrix of in this particular row. I'm going to delete the element at that index too. So that might look a little tricky. It's not, in the sense that it's the same idea as deleting a value of a list. So if we parenthesize it this way, it would make more sense, because I'm going to look at this particular list and I'm just going to get rid of the element at that particular index call, right? But in practice, we wouldn't have the parentheses there. We'll just say, we have this nice shorthand that just says, get rid of whatever is at matrix R call. And then, of course, at the end of this, I want to return my matrix. And that's it. The balloons can come down. We get to do the science now, because as we've seen throughout the course, if we plan the code right, we modularize it effectively, then the code kind of just snaps shut at the end, where we scan through this and we realize that we've written all of the functions that we need to write. And you can see all the functions and functions up py have been fleshed out. So then it's just a matter of saying, well, we need to figure out how to read in a matrix from a file and then process it and do a little bit of I/O, but then I can make my tree and then, in theory, visualize the tree. There's just one problem with that, which is that I neglected one function. And when you look at UPGMA, you can say, well, it seems like we implemented everything. But I'm missing one single function, which is going to take, it's a node method. So when you give it a node, it counts the number of leaves in the tree that is rooted at that node. So if I'm at a leaf, count leaves should return 1. If my node is an internal node, like the root of the tree, it should return then the number of leaves beneath that node in the tree. So sometimes it's going to return 1, sometimes it's going to return 100. And I need a function that's going to, or a method that's going to answer that question for me. The problem is that there's a very natural way of writing this, but it's going to depend upon a concept that we have yet to see in the course. So that's what's fun about this, because we continue, even as far as we are into this, we get to continue to unravel new concepts. So that's what we're going to have to save for next time, is how is it that we write this function? And it's going to require us to learn quite a bit more about an algorithmic concept called recursion that's going to be useful, very useful, anytime we want to do something like this where we have, a collection of data that is, in a sense, recursive, in that a node class represents edges by saying I also have two references to nodes as well as part of my attributes. I have a child1 reference and a child2 reference. And those two references refer to nodes that constitute the edges. So because we have established the class itself thinking in this way, as the edge connections are node to another node that's another instance of itself, this is going to allow us to write a lot of functions around trees that are going to leverage this idea. So how this function of counting the number of leaves is going to work is to say, I don't know how many leaves I have in this tree, but I do know one thing, and that is if I have 100 leaves in my tree, it's because there's some number coming from my left child and there's some number coming from my right child. So I might have 47 from the left child and I might have 53 from the right child. And I'm going to solve the problem by delegating this to my two children and saying, each of you go tell me how many leaves you have and then come and report back. And so it turns out that modern languages have fantastic support for writing functions like this. And we're going to see them in a variety of contexts as a way of resolving this one function that we have remaining in our implementation of UPGMA. We'll do that as well as figuring out, once I've got a tree, how do I visualize it? That's going to require us to do something like, I've got a tree. Does that mean I can write the tree to a file? Because then if I have it in a file, something like, I could use AI to write a huge R pipeline that's just going to make beautiful visualizations for me, which is what we should do. And so we will see all of that, but we need, of course, to save it for next time. So I'll plan on seeing you then. And until then, as always, happy coding.